Hey folks, we're back for another episode of ML for Noobs, and this time we're going to be doing a recap of that last bit from lesson 2, that bit around linear regression. Now, there's certain aspects I got and certain aspects I didn't get, and I want to make sure I get this down, right? You need to make sure that you're completely clear on the basics, because any sort of confusion that you have right now will just get exacerbated the more material you plow through. So getting it clear up front is very important, and that's what I want to do in this video, is just go through the parts of the lesson that I didn't get last time. So just go over the second half of that entire lesson and go through the parts that I didn't get and try to understand that in more detail. And so no real structure for this take. We're just going to go through it and see what happens. All right. Any point of confusion, I'll explain. I'll go through again and again until I actually get it. That's it. Let's dive right in. So
it's not just for school kids. Go to Khan Academy, Jeremy. Find the concept you need a refresher on, and he explains things really well. So I strongly recommend checking that out. So remember, I'm just a philosophy student, right? So I all the time I'm trying to either remind myself about something or I never learn something, and so we have the whole internet to teach us these things. So I'm going to rewrite this slightly. Y equals A1x plus A2. So let's just replace B with A2. Let's give it a different name. Okay. So there's another way of saying the same thing. And then another way of saying that would be if I could multiply A2 by number 1. Okay. This still is the same thing. Okay. And so now at this point, I'm actually going to say, let's not put number 1 there, but let's put an x1 here and an x2 here, and I'll say x2 equals 1. Okay. So far, this is not, this is pretty early high school math. This is multiplying by 1, which I think we can handle. Okay. So these two are equivalent with a bit of renaming. Now, in machine learning, we don't just have one equation, we've got lots, right? So if we've got some data that represents the temperature versus the number of ice creams sold, then we kind of have lots of dots. And so each one of those dots, we might hypothesize, is based on this formula, y equals a1x1 plus a2x2, right? And so basically there's lots of, so this is our y, this is our x. There's lots of values of y, so we can stick a little I here. And there's lots of values of x, so we can stick a little x here, okay? So the way we kind of do that is a lot like NumPy indexing, right? Rather than things in square brackets or PyTorch indexing, rather than things in square brackets, we kind of put them down here in our kind of in the subscript.
So let's be clear what he's saying right here. He's saying originally you thought you would plot temperature against number of ice creams, and here for any temperature you would have a certain number of ice creams sold, right? And this would represent a single data point. So any x here would have a corresponding y, and that would represent 1 point. However, you have many points, and so as a result, you're going to have, again, same formula. So essentially, you can, like, the minimum number of points required to draw a straight line is actually 2 points. Have any 2 points, and you can get, a straight line formula. So you would have a gradient, you would have a y-intercept. So the bigger point that he's trying to make here, or that he is making here, Mr. Jeremy, is that I have a bit of a cold, by the way. I don't know if you hear like a lot of snot and excuse me blowing my nose, and now you know why. Anyway, these are the sort of sacrifices that I'm making for learning, right? Even when I'm sick, I'm still doing these videos. That's what you get. Hard work, baby. Anyway, so back to the point. So what I'm saying is, you could have multiple points. Multiple points have multiple equations, and so you would have multiple gradients with multiple y-intercepts. And so y equal a1x1 plus a2x2 applies when you're talking about a single. So first of all, let's address why you have a1x1, a2x2, and not more. Like you could have a3x3, right? And that is actually a function of what the shape of the line looks like. So a line is going to be a1x1 plus a2x2. A quadratic equation, so squiggly line, would be, or a cone-shaped figure would be a1x1 plus a2x2 plus a3x3. So it'd have 3 components to describe what a quadratic equation would look like. You need 3 points. And so if you're doing something of a higher order, like a higher order function, you would have more points. And so you would have more of these coefficients. I think that's what they call them. So a constant multiplied by x, and the actual order would be different. So you'd have x plus x squared plus x cubed plus x to the power 4 and so on. So anyway, so the number of a1, a2 is actually a function of whether it's a line or it's not. But since we're only talking about lines here, you're only ever going to have a1x1 and a2x2. Okay? That you're only ever going to have two, a1 and a2. However, you can have more data points, and that's the point that he's trying to make here, is that you can have more data points, and so in order to express those data points, you vary the like that little subset indicator that he put over here. So you'd have a1 x1, yeah, but there's xi comma 1, and then subset I depends on which data point you're looking at. All right, take it away.
Okay, so this is now saying there's actually lots of these different yi's based on lots of different xi1 and xi2. Okay, but notice there's only one of each of these. Right? So these things here are called the coefficients or the parameters. So
and the greater point here is that you only have a1 and a2 because you're going to take all of those data points and generate from those a line of best fit that has a single a1 and a single a2. So a single gradient and a single y-intercept. That's the point.
This is our linear equation, and this is still, we're going to say that every xi2 is equal to 1. Okay? Why did I do it that way? Because I want to do linear algebra. Why do I want to do linear algebra? Well, one reason is because Rachel teaches the world's best linear algebra course. So if you're interested, check out computational linear algebra for coders. So it's a good opportunity for me to throw in a pitch for this free course, which you might no money, but never mind. But more to the point right now, it's going to make life much easier, right? Because I hate writing loops. I hate writing code, right? I just want the computer to do everything for me. And anytime you see like these little I subscripts, that sounds like you have to do loops and all kinds of stuff. But what you might remember from school is that when you've got like two things being multiplied together, and then they get added up, that's called a dot product. And then if you do that for lots and lots of different numbers I, then that's called a matrix product. So in fact, this whole thing can be written like this. Rather than lots of different yi's, you can say there's one vector called y, which is equal to one matrix called x times one vector called a. Now at this point, I know a lot of you don't remember that. So that's fine, we have a picture to show you. I don't know who created this, I do. Somebody called Henri Stouts created this fantastic thing called matrix multiplication.xyz. And here we have a matrix by a vector, and we're going to do a matrix vector product. Go. That times that times that plus plus plus, that times that times that plus plus plus, that times that times that plus plus plus. Finished. That is what matrix vector multiplication does. In other words, it's just that, except his version is much less messy. Okay, so let's, this is actually an excellent spot to have a little break and find out what questions we have coming through our students. What are they asking, Rachel?
Okay, hang on. So that multiplying thing looks matrix multiplication dot xyz. Okay, so you have a 3 by 3 matrix multiplied by a 3 by 1. The outcome is going to be a 3 by 1. Now remember that from somewhere. It says you ignore the innermost sizes and you just look at the top, the outside. So you have 3 by x, whatever that x is, doesn't actually matter. Because if you have x by y, the outcome is going to be 3 by y. So 1. It'll take the width, if you like, from the second one, and the length from the first one, the height from the first one. Okay, anyway, that's actually besides the point. The bigger point here is that he put x here and kept a as a vector, and yeah, that makes sense, right? Because your a is going to be fixed. Your a is going to be the fixed amount. It's going to be like a1 to a2, so it's going to be a vector with two rows, and it would have a1 on top and a2 on the bottom. And then when you multiply x by it, what's essentially going to happen is you're going to have let's see if we can go back just a little bit.
Now, created this fantastic thing called matrix multiplication.xyz, and here we have a matrix
Just
by a vector, and we're going to do a matrix vector product. Go.
Alright, so here you can see what's happening is you took a, so the numbers up there are actually a, 2, 6, 1, and so a was 2, 6, and 1. So a is multiplied by x row 0, column 0. So xi 1, xi 2, xi 3. Okay? and I is equal to 0 or 1. I don't know what the basis is. So the first row is going to be 1, for instance. The second is going to be 2, and so on. So x1, 1, x1, 2, x1, 3, x2, 1, x2, 2, x2, 3, and so on. And so yeah, they are functionally equivalent.
His version is much less messy. Okay, so let's this is actually an excellent spot to have a little break and find out what questions we have. And then you should not, and we'll learn about some of them during learn error. So get a small nothing. Try it. I found a situation in practice where I needed to do that. I found it always just works fine for me.
Once you unfreeze and retrain with 1% 34, which I find surprising, I had assumed that the model.
Just like this is for anything, I think the confusion here is that we often use a trained equals false. This is a bit unfair. This thing that, right, it really wants you to send it a whole equation to do n, is we're going to try it, we're going to try and fit this architecture to some data. So let's jump into a notebook and generate some dots, right, and see if we can get it to fit a line somehow. And the somehow is going to be using something called SGD. What is SGD? Well, there's two types of SGD. The first one is where I said in lesson 1, hey, you should all try building these models and trying to come up with something cool. And you guys all experimented and found really good stuff. So that's where the S would be student. That would be student gradient descent. So that's version 1 of SGD. Version 2 of SGD, which is what we're going to talk about today, is where we're going to have a computer try lots of things and try and come up with a really good function. And that was called stochastic gradient descent. The other one that you hear a lot in the, on Twitter is stochastic grad student descent. So that's the other one that you hear. So we're going to jump into lesson 2 SGD. And so we're going to kind of go bottom up rather than top down. We're going to create the simplest possible model we can, which is going to be a linear model. And the first thing that we need is we need some data. And so we're going to generate some data. The data we're going to generate looks like this. So this might represent temperature, and this might represent number of ice creams you sell, or something like that. And we're going to create some synthetic data that we know is following a line. And so as we build this, we're actually going to learn a little bit about PyTorch as well. So basically, the way we're going to generate this data is by creating some coefficients. A1 will be 3, and A2 will be 2. And we're going to create some, like we looked at before, basically a column of numbers for x's and a whole bunch of ones. And then we're going to do this, x at a. What is x at a? X at a in Python means a matrix product. Between x and a. It actually is even more general than that. It can be a vector product, a matrix vector product, a matrix product, or a matrix product. And then actually in PyTorch specifically, it can mean even more general things. We'll get into higher rank tensors, which we will learn all about very soon. Right? But this is basically the key thing that's going to go on in all of our deep learning. The vast majority of the time, our computers are going to be basically doing this, multiplying numbers together and adding them up, which is a surprisingly useful thing to do. Okay, so we basically going to generate some data by creating a line, and we're going to add some random numbers to it. But let's go back and see how we created x and a. So I mentioned that we've basically got these two coefficients, 3 and 2, and you'll see that we've wrapped it in this function called tensor. You might have heard this word tensor before. Who's heard the word tensor before? About 2/3 of you. Okay, so it's one of these words that sounds scary, and apparently if you're a physicist, it actually is scary, but in the world of deep learning, it's actually not scary at all. Tensor means array. Okay, it means array. Specifically, it's an array of a regular shape, right? So it's not an array where row 1 has 2 things and row 3 has 3 things and row 4 has 1 thing, what we call a jagged array. That's not a tensor. A tensor is any array which has a rectangular or cube or whatever, a shape where every element, every row is the same length, and then every column is the same length. So 4 by 3 matrix would be a tensor. A vector of length 4 would be a tensor. A 3D array of length 3 by 4 by 6 would be a tensor. That's what tensor is. Okay? And so we have these all the time. For example, an image is a 3-dimensional tensor. It's got number of rows by number of columns by number of channels, normally red, green, blue. So for example, a kind of a VGA picture would be 640 by 480 by 3. Or actually, we do things backwards. So when people talk about images, they normally go width by height. But when we talk mathematically, we always go number of rows by number of columns. So it would actually be 480 by 640 by 3. And that will catch you out. We don't say dimensions, though, with tensors. We use one of two words. We either say rank or axes. Rank specifically means how many axes are there, how many dimensions are there. So an image is generally a rank 3 tensor. So what we've got here is a rank 1 tensor, or also known as a vector. Right? But like in math, people come up with slightly different words. Well, actually, no, they come up with very different words for slightly different concepts. Why is a 1-dimensional array a vector, and a 2-dimensional array is a matrix, and a 3-dimensional array, does that even have a name? Not really. Doesn't have a name. Like, it doesn't make any sense. Whereas in with computers, we try to have some simple, consistent naming conventions. They're all called tensors. Rank 1 tensor, rank 2 tensor, rank 3 tensor. You can certainly have a rank 4 tensor. If you've got 64 images, then that would be a rank 4 tensor of 64 by 480 by 640 by 3, for example. So tensors are very simple. They've just been arrays. And so in PyTorch, you say tensor, and you pass in some numbers, and you get back, in this case, just a list. I get back a vector. Okay. So this then represents our coefficients, the slope and the intercept of our line. And so remember, we're not actually going to have a special case of ax plus b. Instead, we're going to say there's always this second x value, which is always 1. You can see it here, always 1, which allows us just to do a simple matrix vector product. Okay, so that's A. And then we're going to generate this x array of data. Just going to have we're going to put random numbers in the first column and a whole bunch of ones in the second column. So to do that, we basically say to PyTorch, create a rank 2 tensor. Actually, no, sorry, let's start again. We say to PyTorch that we want to create a tensor of n by 2. So since we passed in a total of 2 things, we get a rank 2 tensor. The number of rows will be n, and the number of columns will be 2. And in there, every single thing in it will be a 1. That's what torch.ones means. And then, this is really important, you can index into that, just like you can index into a list in Python, but you can put a colon anywhere. And a colon means every single value on that axis, or every single value on that dimension. So this here means every single row. And then this here means column 0. So this is every row of column 0. I want you to grab a uniform random number. And here's another very important concept. In PyTorch, anytime you've got a function that ends in an underscore, it means don't return to me that uniform random number, but replace whatever this is being called on with the result of this function. So this takes column 0 and replaces it with a uniform random number between -1 and 1. So there's a lot to unpack there, right? But the good news is those 2 lines of code, plus this one, which we're coming to, cover 95% of what you need to know about PyTorch. How to create an array, how to change things in an array, and how to do matrix operations on an array. Okay, so there's a lot to unpack, but these small number of concepts are incredibly powerful. So I can now print out the first 5 rows. Okay, so column 5 is standard Python slicing syntax to say the first 5 rows. So here are the first 5 rows, 2 columns looking like my random numbers and my ones. So now I can do a matrix product of that x by my a, add in some random numbers, add a bit of noise, and then I can do a scatter plot. And I'm not really interested in my scatter plot in this column of ones. Right? They're just there to make my linear function more convenient. So I'm just going to plot my 0 index column against my y's, and there it is. PLT is what we universally use to refer to the plotting library matplotlib. And that's what most people use for most of their plotting in Python. In scientific Python, we use matplotlib. It's certainly a library you'll want to get familiar with because being able to plot things is really important. There are lots of other plotting packages. Lots of them, the other packages are better at certain things than matplotlib. But like matplotlib can do everything reasonably well. Sometimes it's a little awkward, but for me, I do pretty much everything in matplotlib because there's really nothing it can't do. Even though some libraries can do other things a little bit better or a little bit prettier. But it's really powerful. So once you know matplotlib, you can do everything. So here I'm asking matplotlib to give me a scatter plot with my x's against my y's, and there it is. Okay, so this is my my dummy data representing like temperature and ice cream sales. So now what we're going to do is we're going to pretend we're given this data, and we don't know that the values of our coefficients are 3 and 2. So we're going to pretend that we don't need that. We have to figure them out. Okay. So how would we figure them out? How would we draw a line to fit to this data? And why would that even be interesting? Well, we're going to look at more about why it's interesting in just a moment. But the basic idea is this: if we can find, this is going to be kind of perhaps really surprising. But if we can find a way to find those two parameters to fit that line to those, how many points were there? N was 100. If we can find a way to fit that line to those 100 points, we can also fit these arbitrary functions that convert from pixel values to probabilities. It'll turn out that this techniques that we're going to learn to find these two numbers works equally well for the 50 million numbers in ResNet 34. So we're actually going to use an almost identical approach. So that's this, and this is the bit that I found in previous classes people have the most trouble digesting. Like I often find even after week 4 or week 5, people come up to me and say, I don't get it. How do we actually train these models? And I'll say, it's SGD. It's that thing we saw in the notebook with two numbers. It's like, yeah, but we're feeding a neural network. It's like, I know, and we can't print the 50 million numbers anymore, but it is literally identically doing the same thing. And the reason it's hard to digest is that the human brain has a lot of trouble conceptualizing what an equation with 50 million numbers looks like and can do. So you just kind of, for now, will have to take my word for it. It can do things like recognize teddy bears. You know, these functions turn out to be very powerful. And we're going to learn a little bit more in just a moment about how to make them extra powerful. But for now, this thing we're going to learn for these two numbers is the same thing that we've just been using to fit 50 million numbers. Okay, so we want to find what PyTorch calls parameters, or in statistics you often get called coefficients, these values A1 and A2. We're going to find these parameters such that the line that they create minimizes the error between that line and points. So in other words, if we created, if the A1 and A2 we came up with resulted in this line, then we'd look and we'd see like how far away is that line from each point. And we'd say, oh, that's quite a long way. And so maybe there was some other A1 or A2 which resulted in this line. And then we'd say like, oh, how far away is each of those points? And then eventually we come up with we come up with this line, and it's like, oh, in this case, each of those is actually very close. Right? So you can see how in each case we can say how far away is the line at each spot away from its point, and then we can take the average of all those, and that's called the loss. Right? That is the value of our loss. Right? So you need some mathematical function that can basically say how far away is this line from those points. For this kind of problem, which is called a regression problem, a problem where your dependent variable is continuous, so rather than being grizzlies or teddies, it's like some number between -1 and 6. This is called a regression problem. And for regression, the most common loss function is called mean squared error, which pretty much everybody calls MSE. You may also see RMSE, just root mean squared error. And so the mean squared error is a loss. It's the difference between some prediction that you've made, okay, which is like the value of the line, and the actual number of ice cream sales. And so in the mathematics of this, people normally refer to the actual, and then we call it y, and the prediction, they normally call it y hat, as in they write it like that. And so what I try to do, like when we're writing something like a mean squared error equation, there's no point writing ice cream here and temperature here, because we want to apply that to anything. So we tend to use these like mathematical placeholders. So the value of the mean squared error is simply the difference between those two squared, right? And then we can take the mean, because remember, that is actually a vector, or what we now call a rank 1 tensor. And that is actually a rank 1 tensor. So it's the value of the number of ice cream sales at each place. Right? So when we subtract one vector from another vector, we're going to be learning a lot more about this, but that's something called element-wise arithmetic. In other words, it subtracts each one from each other. And so we end up with a vector of differences. And then if we take the square of that, it squares everything in that vector. And so then we can take the mean of that to find the average square of the differences between the actuals and the predictors. So if you're more comfortable with mathematical notation, what we just wrote there was the sum of, wait a minute, we do it, y hat minus y squared over n. Right? So that equation is the same as that equation. So one of the things I'll note here is I don't think this is, more complicated or unwieldy than this. Right? But the benefit of this is you can experiment with it. Like once you've defined it, you can use it. You can send things into it and get stuff out of it and see how it works. Right? So for me, most of the time, I prefer to explain things with code rather than with math, right? Because I can actually, they're the same. As in this case, at least in all the cases we'll look at, they're exactly the same. They're just different notations for the same thing. But one of the notations is executable. It's something that you can experiment with, and one of them is abstract. So that's why I'm generally going to show code. So the good news is if you're a coder with not much of a math background, actually you do have a math background because code is math. Right? If you've got more of a math background and less of a code background, then actually a lot of the stuff that you learn from math is going to translate very directly into code. And now you can start to experiment really with your math. Okay, so this is a loss function. This is something that tells us how good our line is. So now we have to kind of come up with what is the line that fits through here. So remember, we don't know. We have to pretend we don't know. So what you actually have to do is you have to guess. You actually have to come up with a guess. What are the values of A1 and A2? So let's say we guessed that A1 and A2 are both 1. So this is our tensor. A is 1, 1. Right? So here is how we create that tensor. And I want to write it this way because you'll see this all the time. Like written out, it should be 1.0. Oh, sorry, it looks like minus 1. Minus 1. Written out fully, it would be minus 1.0, 1.0. Like that's written out fully. We can't write it without the point because that's now an int, not a floating point. So that's going to spit the dummy if you try to do calculations with that in neural nets. Right? I'm lazy. I'm far too lazy to type .0 every time. Python knows perfectly well that if you add a dot next to any of these numbers, then the whole thing is now floats. Right? So that's why you'll often see it written this way, particularly by lazy people like me. Okay, so A is a tensor. You can see its floating point. You see, like even PyTorch is lazy. They just put a dot at the bottom of the 0. Right? But if you want to actually see exactly what it is, you can write dot type, and you can see it's a float tensor. Okay. And so now we can calculate our predictions with this like random guess, x and a, matrix product of x and a, and we can now calculate the mean squared error of our predictions and our actuals, and that's our loss. Okay, so for this regression, our loss is 8.9. And so we can now plot a scatter plot of x against y, and we can plot the scatter plot of x against y hat, our predictions, and there they are. Okay, so this is the 1, minus 1 line, minus 1, line, and here's our actuals. So that's not great, it's not surprising, it's just a guess. So SGD, or gradient descent more generally, and anybody who's done any engineering or probably computer science at school will have done plenty of this, like Newton's method, whatever, it's all the stuff that you did at university. If you didn't, don't worry, we're going to learn it now. It's basically we're taking this guess and trying to make it a little bit better. So how do we make it a little bit better? Well, there's only two numbers, right? And the two numbers are the intercept of that orange line and the gradient of that orange line. So what we're going to do with gradient descent is we're going to simply say, what if we change those two numbers a little bit? What if we made the intercept a little bit higher or a little bit lower? What if we made the gradient a little bit more positive or a little bit more negative? So there's like 4 possibilities. And then we can just calculate the loss for each of those 4 possibilities and see what works. Did tilting it up or down make it better? Did tilting it more positive or more negative make it better? And then all we do is we say, okay, well, whichever one of those made it better, that's what we're going to do. And that's it, right? But here's the cool thing, for those of you that remember calculus, you don't actually have to move it up and down and round about. You can actually calculate the derivative. The derivative is the thing that tells you would moving it up or down make it better, or would rotating it this way or that way make it better. Okay? So the good news is, if you didn't do calculus or you don't remember calculus, I just told you everything you need to know about it, right? Which is that it tells you how changing one thing changes the function. Right? That's what the derivative is. Kind of, not quite strictly speaking, but close enough, also called the gradient. Okay, so the gradient or the derivative tells you how changing A1 up or down would change our MSE, how changing A2 up or down would change our MSE, and it does it more quickly. It does it more quickly than actually moving it up and down. Okay? So, in school, unfortunately, they forced us to sit there and calculate these derivatives by hand. We have computers. Computers can do that for us. We are not going to calculate them by hand. Instead, we're going to call .grad. On our computer, that will calculate the gradient for us. So here's what we're going to do. We're going to create a loop. We're going to loop through 100 times, and we're going to call a function called update. That function is going to calculate y hat, our prediction. It is going to calculate loss, our mean squared error. From time to time, it will print that out so we can see how we're going. It will then calculate the gradient. And in PyTorch, calculating the gradient is done by using a method called backward. So you'll see something really interesting, which is mean squared error was just a simple standard mathematical function. PyTorch, for us, keeps track of how it was calculated and lets us calculate the derivative. So if you do a mathematical operation on a tensor in PyTorch, you can call backward to calculate the derivative. What happens to that derivative? It gets stuck inside an attribute called .grad. Backward to calculate the derivative. What happens to that derivative? It gets stuck inside an attribute called .grad. So, to calculate the derivative. What happens to that derivative? It gets stuck inside an attribute called .grad. So, I'm going to take my coefficients A, and I'm going to subtract from them my gradient. And there's an underscore here. Why? Because that's going to do it in place. So it's going to actually update those coefficients A to subtract the gradients from them, right? So why do we subtract? Well, because the gradient tells us if I move the whole thing downwards, the loss goes up. If I move the whole thing upwards, the loss goes down. So I'm going to like do the opposite of the thing that makes it go up. Thing downwards, the loss goes up. If I move the whole thing upwards, the loss goes down. So I'm going to like do the opposite of the thing that makes it go up, right? So with our loss, we want our loss to be small. So that's why we have to subtract. And then there's something here called LR. LR is our learning rate. And so literally all it is the thing that we multiply by the gradient. Why is there any LR at all? Let me show you why. Let's take a really simple example. A quadratic. And let's say your algorithm's job was to find where that quadratic was at its lowest point. And so how could it do this? Well, just like what we're doing now, the starting point would just be to pick some x value at random, and then pop up here to find out what the value of y is. Okay, that's the starting point. And so then it can calculate the gradient, and the gradient is simply the slope. Right? It tells you moving in which direction is going to make you go down. And so the gradient tells you you have to go this way. So if the gradient was really big, you might jump this way a very long way. So you might jump all the way over to here, maybe even here, right? And so if you jump over to there, then that's actually not going to be very helpful, because then you see, well, where does that take us to? Oh, it's now worse, right? We jumped too far. So we don't want to jump too far, so maybe we should just jump a little bit, maybe to here. And the good news is that is actually a closer. And so then we'll just do another little jump. See what the gradient is into another little jump. That takes us to here. Another little jump. That takes us to here. Here. Right? So in other words, we find our gradient to tell us kind of what direction to go, and like, do we have to go a long way or not too far? But then we multiply it by some number less than 1, so we don't jump too far. And so hopefully at this point, this might be reminding you of something, which is what happened when our learning rate was too high. So do you see why that happened now? Our learning rate was too high, meant that we jumped all the way past the right answer, further than we started with, and it got worse and worse and worse. So that's what a learning rate too high does. On the other hand, if our learning rate is too low, then you just take tiny little steps. And so eventually you're going to get there, but you're doing lots and lots of calculations along the way. So you really want to find something where it's kind of either like this, or maybe it's kind of a little bit backwards and forward. Maybe it's kind of like this. Something like that. You know, you want something that kind of gets in there quickly, but not so quickly it jumps out and diverges, not so slowly that it takes lots of steps. So that's why we need a good learning rate. And so that's all it does. So if you look inside the source code of any deep learning library, you'll find this. You'll find something that says coefficient not subtract learning rate times gradient. And we'll learn about some we'll learn about some easy but important optimizations we can do to make. Then we'll just do another little jump. See what the gradient is into another little jump. That takes us to here. Then that's actually not going to be very helpful, because then you see, well, where does that take us to? Oh, it's now worse. Right? We jumped too far. So we don't want to jump too far, so maybe we should just jump a little bit, maybe to here. And the good news is that is actually a little bit closer. And so then we'll just do another little jump. See what the gradient is into another little jump. That takes us to here. Another little jump. That takes us to here. Here. Right? So in other words, we find our gradient to tell us kind of what direction to go, and like, do we have to go a long way or not too far? But then we multiply it by some number less than 1, so we don't jump too far. And so hopefully at this point, this might answer further than we started with, and it got worse. And worse and worse. So that's what a learning rate is. Something, you know, you want something that kind of gets in there quickly, but not so quickly it jumps out and diverges, not so slowly that it takes lots of steps. So that's why we need a good learning rate. And so that's all it does. So if you look inside the source code of any deep learning library, you'll find this. You'll find something that says coefficient dot subtract learning rate times gradient. And we'll learn about some we'll learn about some easy but important optimizations we can do to make this go faster. That's basically it. There's a couple of other little minor issues we don't need to talk about now, one involving zeroing out the gradients, another involving making sure that you turn gradient calculation off when you do the SGD update. If you're interested, you can discuss them on the forum. Or you can do our Introduction to Machine Learning course, which covers all the mechanics of this in more detail. But this is the basic idea. So if we run up